Let us examine the solution you just have derived. The first part of the solution is a constant, multiplied with time. This part indicates the average velocity of the bar. The part after the summation will describe the deformation of the pile per mode. Each mode is described by three components. The first component is a constant per mode and describes the amplitude of the mode. The second component describes the shape of the mode, better known as the mode shape. And the third component describes the harmonic behavior and time of that mode. The harmonic behavior depends on the eigenfrequencies of that mode. When we fill in the parameters of the pile, the result will look like this. And we can keep expanding this equation to infinity. Now we will animate the results you just have calculated. It is clearly visible that the wave propagates as a real caterpillar. Only the part of the pile where the wave is located moves. Since there is no restricting force, the beam can move forever after a single blow of the hammer. Of course, in reality this is not the case. A lot of energy radiates into the soil, and the wave will damp out over time. It is important for you to understand that the pile is driven by waves and is not instantaneously driven after getting hit. Another important aspect to understand is the significance of the boundary conditions. What will happen when we interchange the free boundary for a fixed one? For sure we know that the bar cannot move anymore at this location. But also another fact will happen here. As shown in the animation, when the wave reaches the end, the compressional amplitude will double. This happens because upon reflection, the strain will be the summation of a part of the wave that is still traveling towards the end, and a part of the wave that has already reflected. Since the strain will double and is linearly proportional to the stress will double as well. This is important to know because it is important to know what the maximum stresses might be in your pile when you hit a solid layer. For example, when you will hit rocks during driving. You have learned that the stresses can double in this case. So what happens then? The high stresses can lead to crushing of the concrete piles. In this case, the pile loses strength, which can damage the whole structure that is built on top of it. The wave equation is not only important for driving of piles, but it is used in many civil applications, such as non-destructive testing or health monitoring of structures. Even material parameters can be derived from waves and their reflections. But also in many non-civil applications, the wave equation is of importance. You might, for example, think of acoustic calculations or shock waves from explosions. This was it for today. Thank you for watching.